In this tutorial, we're going to show how to, using the PuMA GUI, calculate just very basic phenomenological properties, just volume fraction and surface area. So first thing is just open up a terminal. We just need to launch the PuMA GUI. Open up a terminal, type in conda activate PuMA, and then run the PuMA GUI.sh command. Now the PuMA GUI will launch. Of course, in order to calculate any of these properties, we need to have a material that we're working with. If you want to know how to import, export, generate, etc., go reference the other tutorials. For now, we're just going to import a very simple microtomography sample, which is a carbon fiber material, which is 200 by 200 by 200. And in this case, the voxel length is important for calculating the surface area, so you have to make sure that that's set correctly. For this material, the correct voxel length is 1.3 times 10 to the minus 6. Of course, this will be different for each tomography case. So to calculate the volume fractions, first thing we might be interested in, for example, in this material, could just be the porosity. So I'm going to create a 3D rendering just so you have a sense of what this material looks like before we get into the material calculations. So here you can see that this is a carbon fiber material that has a porosity of, I don't know, maybe 85%, something like that. So let's see if that, let's see if we get that. If we go to material properties, porosity, now we have to select the grayscale range of the void phase. So in this case, the grayscale range of the void phase is going to be between 0 and 89. Now you'll get this through going through the thresholding-based segmentation process, which I outlined in another tutorial video, or if you imported a already segmented tomography, this range would probably just be 0 to 0, since these values are inclusive. So grayscale range 0 to 90, calculate, and we see our porosity is 0.78, so about 79% porous. We would get the same answer, for example, if we went to material properties, volume fraction, and just looked at the volume fraction of the void phase, which is 0 to 89. And again, we get that 0.89%, 0.789% porosity, 0.78 porosity. So if we wanted to calculate the volume fraction of the material phase, we can select that as 90 to 255 in the case of this particular tomography sample. And we can see that we have a volume fraction here of 0.21. So moving on to surface area, if you go to material properties, surface area. Now, there are a couple different surface representations that you can use for the surface area. It's either marching cubes or cubrile. Now, let me use the visualization tool actually to visualize the difference here. If I were to create a volume rendering of this material, I'll go ahead and do that. Here we go. Now you can see what the material looks like in cubrile form. So by cubrile form, I mean this voxelated structure that looks like something out of Minecraft. The surface area, if you use this cubrile form, is actually going to go into each of these voxels and count the surface area of the exposed face. Now, as it turns out, you may want that for specific applications, but overall, normally this is not actually a very good estimation of the surface area. For example, if you do the math on a sphere, obviously there's an analytical solution for what the surface area of a sphere is. And if you use this voxelized form in order to calculate the surface area, you end up actually calculating the area of the projection of that sphere onto the 6 faces of this cube. So it's actually 6 times the area of a circle with the same radius as your sphere, which ends up being an overestimation by 50%. It ends up being a 50% overestimation of the surface area. So typically we don't use the cubrile option, but we've left it in there just in case for a specific application it may be useful. So instead we use marching cubes, which uses a triangulation of the surface brought about by the marching cubes algorithm in order to estimate what the surface area is. So for the marching cubes to run, we have to specify what the grayscale range is of the void phase in this case. So the void phase we're going to say is between 0 and 89 inclusive. And then we're going to begin calculation. And you see here we end up with the surface area as well as the specific surface area. So the surface area is in meters squared. That's just the raw actual surface area in this particular tomography sample. And if you were to import a tomography sample that was much larger, instead of just simply 200 cubed, if this was 1,000 cubed sample, you'd obviously get a different raw surface area. The specific surface area, on the other hand, is a more fundamental material parameter, and it is the surface area per unit volume. So it's meters squared over meters cubed, resulting in a total of 1 over meters. And it should be, as long as your sample is a representative volume, which in the case, of course, of this small 200 cube sample, it probably would not be, then this should be independent of your sample size. And in this case, we end up with something like 40,000 as our specific surface area. If you are trying to calculate the surface area of a multi-phase material and you are interested in, for example, just the exposed area of phase 1 to the void phase, then calculating the surface area actually gets a lot more complicated and is not really feasible for the GUI calculation. What I would recommend instead is to reference the multi-phase tutorial in the Python version of the code, which can be found as a Jupyter notebook. And in there, we go through more detail on how to calculate the various types of surface area that you may be interested in. So that's it for the volume fraction and surface area tutorial. If anything here didn't work properly for you, or if you have any questions or just would like to reach out to us for any reason, my email is found here, joseph.ferguson@stanford.edu. You can also email federico.semeraro@nasa.gov, or both of us, and we will get back to you as soon as possible if you have any questions.